Hello everybody, I'm going to share projects I recently did and results. Yeah, I'm quite happy with the result, and basic is just a water simulation, and also there's a breakdown. Use Nook to composite the result, and this is some process I will go through later. So basically, this is a workshop I followed on a website named Norman Workshop. I will put the link in the description. So yeah, this is some main part of this process. Basically, okay, I will show separately. Basically, if you put everything in your project, basically if you just put everything like the monster and put a surface and use the flip solver to simulate. Flip solver is a Houdini default fluid solver, and if you use this to simulate, you can get a very decent simulation already. But this is not good enough because the resolution of this simulation is not high enough. This is already like this one. This is already have 5 million. What's this? 4 million or 5 million particles, but it's not have enough details like here, like this. So we need add another effect, which is Whitewater. So this is what Whitewater looks like. So basically, this simulation is combined these two things. This Whitewater is the juicy part, the more detailed, more particles. This I think it's hundreds millions of particles. So it's very a lot particles. And another part is the flip simulation. So you can see here, I put them together. This is basic flip simulation, and based on this simple simulation, you can surface it to a polygon, and so basically it's the base of the simulation, and based on that, we simulate this white water and combine them together to get the final result. So this is a basic workflow, and then we'll go to the little bit details, like what I learned for each step. Okay, I think from beginning we need the ocean. So basically, ocean is very simple. It's just use ocean node, ocean spectrum node, which is Houdini provided node, and basically it you can adjust some parameters. Use this spectrum IFTMA type to get some. I think you can get the wave information like frequency and amplitude to use this information to deform the surface grid. So yeah, this can see this one. Yeah, this is the grid, and this is just spectrum information you get from this node, and you put in this ocean evaluate node, you can get this mode ocean. So it's very easy. And what more? Let's see. And yeah, you can see here she separates the spectrum to two parts. One part is low frequency spectrum, and one part is high frequency spectrum. So basically, we just apply low spectrum, a low frequency spectrum onto the geometry, because you can see if I put the high frequency, actually you cannot see anything because the grid doesn't have enough resolution to see it. Actually, you can see a little bit, but still it loses a lot of information here. So basically, the low frequency spectrum will apply only a low frequency spectrum on the geometry, and apply high frequency spectrum during the render process to apply on the pixel level. Use displacement. So yeah, this will use when in rendering part in material. Okay, I think this is ocean. Yeah, the ocean part is a very good trick. I learned it that you can because the grid at the beginning is very big, but we don't need to use all of this big. So basically, use camera to cutting the range of the surface you need, and so it's very easy. Just use the position and transform to the NDC normalized device coordinate space to get the NDC range, and use this range to get a volume. I use this volume to trim your grid, and after trim you get this. This is what your camera actually can see. All this part. You won't need other part of, you see, it's cutting other part out. So it's very useful. And another trick is use LOD. This is very common especially in real-time rendering. Here also if we see here, basically means it's too far from your camera. Basically, our camera is here. If you're too far of your camera, we don't need so high resolution. So basically, we use the camera track. This is the camera track, and we use the distance from this track to calculate the LOD detail. Like the near to the camera, we will use higher resolution, and the result is, let's see if you can see here, the red one is more high resolution, and the light red is low resolution. Yes, this is LOD part. I think it's very good, very smart trick. So this is the ocean part, and what's next? Ocean, and this is the simulate, and simulate is nothing much. You just put everything in and put your monster animation here, and simulate use this fleet solver. Yeah, you can get the result. And what I learned here is, I learned something. I tried to do some research about this flip solver. What it did, that's this how to simulate a flip generally. And you can see here, this is a catch part. If you catch out, you can see there is some points, particles. Also, there are some field like surface and velocity field. Here. So basically, this method is used named PIC, like particle in cell. So you use particles. I also use field. Field is like volume information to calculate. So basically, they use particles to move step by step, move the particle position step by step, and also use the field, the volume information to calculate the projection. Projection is very important in fluid simulation. And
fluid.
And so basically, here in solver there are two methods. One is fleet, another is epic. By default, it's use epic, and but in this case, sometimes we can use fleet because it's more splashy, so it's more more juicy. But I think it's not very different, and the difference of this different method is that flip basically just it's a optimized method based on the basic PIC method, but epic is a more newer method that use store some more information to get a more accurate result. So anyway, we don't need to know all these details, but what we can do here is where is this? Yeah, inside this, if we allow ourselves to edit this, you can see this sub solver is just a wrap of a DOP solver. Inside is a DOP flip solver, and in the DOP flip solver, there is a node very important in this project, non-divergent node. Basically, what it did is to do the hard work in this simulation is to do projection to reduce this divergence during the simulation. So in this node, we can change this error tolerate. By default, is a very small value, and we don't need it so small. So we use a kind of a little higher value a little bit to make our simulation more efficient. Yeah. And basically this is a simulation, and after simulation we need to surface our basic simulation. So basically it's use this node, right? Particle fluid surface is you put your simulation result in, and it will give you the mesh, and inside you will see it just convert the particles into VDB volume, and then to small volume and convert to polygon. Yeah, this is what we get the surfacing. So after we have the surface, we can render this base part of the simulation. And here is some tricks I learned that how to cache, efficient cache the particles, and also cache the surface and the VDB information. And yeah, you can see here after we get the data, we basically prepare the data. And one trick is to this is still use this camera view frustum to cutting our surface, and so we can get rid of something. And yeah, for cache VDB, we can use like resample to decrease the resolution of this film, especially the velocity film. We don't need so high resolution, and also to write them into 16-bit floats. Yeah, something like that. Yeah, it's very efficient. We reduce a lot of storage. This storage is very helpful. And to cache the particles, I think still we have a lot of there's a lot of methods to use. Like I said, the simulation is two parts. One part is particles, another part is the volume, the cells field information. So here, when we catch the simulation of fluid, we split them to part. One part is just so you can see here, this part is just particles, don't have any field volume, and this part is only volumes without particles. So for particles, basically we can write some attribute using 16-bit float, because we don't need so high precision. So we can just cast it to 16-bit, and also use this convert to VDB points. So basically we use VDB to store these particles. It's a very good strategy. And for volumes, also VDB, we use resample to decrease the resolution of velocity film, and also change notice to change the to decrease the precision to 16-bit float. Use this primitive node and things like that to make our cache more efficient and use less storage. Okay, this is the fleet and fleet surfacing. And after we get our fleet, we start to work on our Whitewater. And yeah, basically, you can see here, there's two parts for Whitewater. One part is it gets from the when the creature come out of the ocean, there will be some water stick on its surface, and it's also dropped from the surface. That's one part. Another part is this big splash. It's basically, need a lot of detail, a lot of particle. So for these two parts, we for the first part we use our master to calculate calculate the area we want to emit more particles. So basically we emit more particles to. So I will just say about the overall flow. So Whitewater basically we don't use this default solver that provided by Houdini. Instead, we create our own solver. So we need to decide where we emit more particles and how to simulate it. So basically, we build this all this simulation by ourselves. And then let's talk about the two parts. One part is that we emit particle from the mountain surface, so we can have this the particles like sticked here and dropped from its surface. So we need to calculate where it has emitted particles and had more particles. So basically, this concrete area, it's calculated use curvature, and this concrete area is negative value. So basically use curvature and to get this area, and then we scatter points on this area and get all these points into the solver to simulate the Whitewater. This is one part. Another part is we use the simulation we already have, like here, like this surface. We have surface our flip like this, and we use this as the base. So basically, this part is just the particles emitted from the tips of the flip surface. So how to get this area? Also we use curvature and also the vorticity and velocity to calculate the area. You can see the vorticity is basically the curve value of the particles, and velocity is the speed, and curvature is basically the tips of the surface. So we have this area, and we learn it, and we use this to scatter particles like this. So we use these scatter particles. Also, we base on the velocity of this simulation, so they are more consistent together. So we put all this into the server and simulate the final Whitewater. And for the server, I think what I need to mention is that the most important thing is you need to make this Whitewater simulation to interact with Collide, like with monster, and also with our basic simulation, basic flip simulation. This is surface. The surface interact with surface. So yeah, this is not very hard. We just put them in and write some code to make it like this to interact, and also to have this water dropping down from the surface. Use some code here. Yeah, it's not very complicated actually if you understand how to do it. And yeah, basically this is how to simulate Whitewater. What else? Okay, after we get another part is this airfield. That is our simulation need to calculate the air disturbance, basically, like wind, how wind influence the particles, and also the movement of the creature will disturb the air. So basically here we use our creature to put them into pyrosolver to get air field, like velocity field. We can visualize here. This is count for the wind and also the movement of the creature to disturb the air. So this is how this disturb influence the velocity field, and we put this velocity field into our white solver to influence our particle simulation to get the right disturbance of this whole simulation. This is very makes sense and very very, how to say, physical accurate. Yeah, this is the Whitewater simulation, and after that we start to render. To render this two part. One part is ocean and flip. The flip is we just render the. It's similar to render ocean. It's just we treat it like a polygon surface, and we just render this. And for Whitewater, we render it through volume. Basically, we rasterize it into a volume. Make here. Okay. Yeah. yeah, we just rasterize into volume and treat it as a volume to render. And in render in Solus, basically we put everything into into different passes, so we can more efficient render them out and composite them in Nuke. So what I can say is that there are basically the geometry setting and rendering setting. What's very important is I found this geometry setting. Let's see the first one here. What is very important is this dicey quality. Basically, this decides how the resolution of displacement of the geometry. So always influence the displacement speed. When we use displacement, its influence is very slow down your performance. So this one is very important and very efficient. Influence a lot for your performance. So if you just preview your rendering, okay, try this one. So, if you want to preview, it's better to decrease. My computer is very lame, so I don't want to try. But basically, you disable this and put this to 0. So basically, this means we don't use any displacement, and this true displays, if we disable it, it just use a bump map instead of displacement, so it's very fast. But if you are rendering, you need to enable this and adjust this parameter to have the balance between performance and quality. Because if it's too high, by default is as 0.5. But if higher, it has more resolution of displacement, especially for the ocean. If you see the displacement, it's very important, but it will really slow down your performance. So this is very important parameter. And for rendering, rendering setting is this comma setting. I think basically it's just samples is very important for rendering. The primary samples, also the secondary samples, and also this limits. It depends on your requirement to adjust these parameters. And this simulation is basically use comma CPU to render. And I think for ocean and this volume whitewater rendering, we can try comma TRPU. I think it's real much faster. Okay. Besides rendering, I'll talk a little about this. Yeah, because there are 4 parts. So basically here we use tops to render in one click. So what I want to say is that here the frames per batch, this value sometimes is very important. Not very important. This means that how many frames we put them together as in one batch to work on. So, for the top, this TOP network, what actually Houdini did is that it will launch I can't find a picture here. Launch instance, Houdini instance in the background. Yeah, I have a like this. He launch this one Hyphen. Basically, it's just a Python environment to accuse all the tasks that they want Houdini to do, and this Husk and also launch this Husk. Husk is a kind of camera render thread to do the rendering part. So basically, every bench it will launch one Hansen and also a render thread to work. And after, if we set it to 3 frames, it will use this one time launch to work on 3 frames, and then you will kill these two, and to launch another new one, a new Hansen thread, and to work on other bench, other frames. So yeah, it's a balance between, because if there are too many frames, it will need higher memories. You see, my computer is my laptop is only have 40 gigabytes, so I cannot afford too many frames together. So I just keep it low, and also so it's a balance. If you have a good device, good computer, you can bench many frames together, so they don't need to kill and launch this instance, this thread, because it needs some time, but it's not very. Yeah, it's very important. And another thing is this total slots. It means you want how many bench are working together. So it also depends on your computer. If your computer is very capable, you can have more slots to work on. Okay, that's it. I think that's what I want to share. Okay, that's it. Yeah, I want to thanks this workshop, and sorry, I forgot the name. Mago Paris. Yeah, who created this workshop, and I learned a lot from this. And actually, I'm a very beginner of Houdini, and I try to share this because I think I can help me to review what I learned and actually help me to practice some English. Anyway, hope you enjoy this. You can learn something or get something from here. Okay, see you next time.